Electrochemical cells generating voltage uh, using redox reactions. So electrochemical cell, galvanic cell, voltaic cell, they all mean the same thing. You're having a redox reaction occur so that electrons are transferred through a wire from the reducing agent over to the oxidizing agent. And in the process, you're generating usable electricity. So by separating the oxidizing agent from the reducing agent, electrons are transferred by an external conducting medium, a wire. So construct a galvanic cell based on this redox reaction. Okay, so the redox reaction here is a spontaneous one. Copper 2 ions will spontaneously take electrons away from zinc to form copper metal and zinc 2 plus, a demonstration we've seen often. So if I dip the zinc strip into the copper sulfate solution, yeah, the copper sulfates, are hungry for electrons, right? So they start grabbing electrons off of the zinc surface, and you start getting a copper coating on the zinc, and zinc ions start going into solution, right? So the zinc metal loses electrons to the copper 2, and you generate zinc ions floating around now. Now, the problem with the way this reaction is set up is there's no way to use this energy, right? This push on the electrons you're giving by having this redox occur. So we need to separate the oxidizing agent from the reducing agent and use a wire. So I put the zinc on the one side and the copper 2 on the other. And in this way, the copper 2 is taking electrons away from the zinc through the wire. So the electrons travel from the zinc over to the copper 2. And zinc on the one side is turning into zinc 2 plus, and on the other side, copper 2 plus is turning into copper. Now, eventually, you build up a charge. You end up with plus charge building up on the zinc side and a negative charge building up on the copper sulfate side, and the electrons stop flowing. So to keep them flowing, we need some sort of conducting instrument that's going to allow the electrons or allow the charge to keep flowing. So this is what a salt bridge is. Or sometimes they use a porous disc, which allows ions to flow across from one side to the other. So a salt bridge completes the electric circuit by putting some sort of non-reactive ions in the salt bridge. So as charge builds up on the one side, the cations run over to the negative side, and the anions run over to the positive side of the electrolytic cell. So we're using potassium chloride here, right? So the potassium ions can't give up any more electrons, and chloride can't take any more. So this is a good conducting medium to use, right? It's kind of like what we used to use, kind of like what we had when we were doing using electrolyte solutions to light the light bulb, right? The ions keep the electrons flowing through the system. So ready, set, go. We stick our conducting medium in here now, right? And as the reaction goes forward, you're building up positive charge on the copper side, and building up a negative charge on the copper side and a positive side on the zinc side. So the chloride ions flow towards the buildup of zinc 2 plus charge, and the cations flow over to where you're building up the sulfate negative charge. And the electrons keep flowing. All right, anode is where oxidation occurs, and the cathode is where the reduction occurs. So there's I don't really like little sayings, but this one I remember. Anox, red cat. Anox. Oxidation occurs at the anode, red cat, reduction occurs at the cathode. All right, so we've got the zinc being oxidized over at the anode, and we've got copper 2 plus being reduced over at the cathode. So it's a picture of a electrolytic cell or a galvanic cell. This is how we generate voltage. So depending on how much a redox reaction this is, how good a taker copper 2 plus is, and how good a giver zinc is, we're going to get a certain amount of push on those electrons. And that's what voltage is. Voltage measures how much shove those electrons have going over from the reducing agent to the oxidizing agent. So here we have zinc losing electrons to copper 2 plus over on the other side. So the wire is going through something that's measuring the voltage, right? So the push on these electrons give me 1.1 volts. So a nice picture here. We got zinc 2 plus being produced over on the one side and copper 2 plus taking electrons becoming copper on the other. So two half reactions, right? Zinc losing electrons, copper 2 gaining electrons down the bottom there. And the salt bridge allows the electrons to flow. Electrons to flow. Flowing electrons. So the anode is where oxidation occurs, the cathode is where reduction occurs. Hard to draw this every time we want to talk about an electrolytic cell. So this is called a cell diagram. And the way this is set up is we go from the anode over to the cathode in terms of what species we encounter, right? So first thing, you've got zinc. Zinc is the thing losing the electrons. Then you have a phase boundary, right? That's what the line represents between the zinc metal turning into the zinc 2 plus in the solution. Then you encounter a salt bridge, right? This is separating the anode from the cathode. Then on the other side, you've got copper 2 plus taking electrons along a phase boundary turning into copper. So this is a shorthand way of writing what's going on in an electrolytic cell. So by convention, you start with the anode and you work your way over to the cathode. Work your way eventually over to the product of the cathode. Product at the cathode. So like I said, voltage, cell potential, electromotive force, right? How much push the electron has as it's going through the wire. How much force it has. So the symbol is script E with a subscript cell indicating what the voltage of the cell is. And the unit is volts. So when you talk about high voltage, you're talking about high energy electrons, big push on the electrons. So a volt is a measure of how much push, right? So it's measured in joules per coulomb. Coulomb is the unit for charge. So how much energy per coulomb does the electron have? Coulomb is equivalent to 1 ampere second. So this is these are synonymous terms, ampere second and coulomb. Ampere is how much current you have. So with electricity, those are the two things you're measuring. What the push on the electron is, what the voltage is, and ampere is how many of those electrons are passing per second. All right, so when all species are in their standard state, this particular cell gives a voltage of 1.1 volts. And later on, we'll talk about what standard state is. It means 1 molar concentration of the zinc ion and 1 molar concentration of the copper 2 ion. Sulfate is just a spectator here.